Hi, this is Jana Ibrahim's video series on bipolar junction transistor. In this video, we will discuss about DC load line. In previous videos, we have discussed the basic transistor characteristic and properties. Now we can start analyzing and designing the DC biasing of a BJT circuit. After watching this video, we should be able to state the purpose of DC biasing circuit. Secondly, plot the DC load line of an amplifier given the value of VCC and resistors. Third, describe the Q point of an amplifier and explain its purpose. A brief description on the world of silicon miniature components. After the development of transistor, the race was on to make minute versions of almost every type of electronic components and circuit, and the race is still on until now. For example, resistor and capacitors could be made on silicon, and this made it possible for entire amplifiers, including its biasing circuitry, to be constructed on a silicon wafer. The rapid advancement of micro and nano manufacturing technology allows millions to trillions transistors and other electronic components to be produced on a single silicon wafer, creating an integrated circuits or ICs with size smaller than a coin. In recent years, we have amplifier circuit placed in our mobile phone, headphones, which are very small in size. The AC operation of a BJT amplifier depends on its initial DC values IB, IC, and VCE. As IB is varied around its initial value, IC and VCE are also varied around their initial values. The function of DC biasing is to set the initial values of IB, IC, and VCE. In other words, biasing is a means of setting initial operating point of the transistor. There are several biasing methods, each to achieve different results. Because that the common emitter is the easiest BJT configuration, here we will discuss the DC load line and related biasing effects using the common emitter configuration. The DC load line is a line that represents every possible combination of IC and VCE for a given amplifier. An example of a DC load line is shown here. The load line indicates there is a unique VCE value for every IC. The load line N at y-axis is labeled I saturation, which represents the ideal value of saturation current for the circuit. This saturated transistor looks as being short circuit from the emitter to collector terminals that resulted in VCE equal to 0, and the KVL equation becomes VCC equal to IC times RC. And by rearranging the equation, we got IC saturation equal to VCC over RC. Meanwhile, at the x-axis, the end of the DC load line is labeled as VCE off, which represents the cutoff voltage. Because in cutoff condition, the emitter and collector is being an open circuit, which means IC equal to 0. Hence, IC times RC is 0, and the KVL equation at the CE loop, which is output of the common emitter circuit, becomes VCE off equal to VCC. A Q point is a point on the DC load line that indicates the values of VCE and IC for an amplifier to rest. It means this is when a transistor does not have an input signal, its output rests at a specific point on the DC load line, hence it is a constant value, which is IC and VCE. The Q point can be easily determined when the DC load line is superimposed on the collector curves of a transistor. The Q point is where the load line intersects the appropriate collector curve. For a linear operation of an amplifier, it is essential to have the Q point at the center of the DC load line. This is because when we have a centered Q point, VCE is half of the value of VCC and IC is half the value of IC saturation, and this Q point is called midpoint bias. Why is it important to have midpoint bias? Here is why. When an AC signal is applied to the base of a transistor, IC and VCE both will vary around the Q point. Hence, centered Q point provide the maximum possible transitions above and below their initial values. Let's think about this. If the Q point is above the center of the load line, the input may cause the transistor to saturate. Hence, parts of the output signal will be clipped off. But if the Q point is below the load line, the transistor may be into cutoff and cause the portion of the signal to be clipped as well. Let's discuss the following example. For a circuit given, solve the input and output parameter for common emitter configuration using graphical approach, which is DC load line. First, we need to identify the input and output loop and parameters for the common emitter configuration. Input loop is base emitter loop and its parameters are RB and VBE. Meanwhile, the output loop is collector emitter loop and its parameters are IC and VCE. Next, the question requires to find IB value. Write the KVL of the BE loop as IB equal to VBB over RB minus VBE over RB. Then, set the VBE to 0 to get IB value at y-axis and set IB equal to 0 to get VBE value at x-axis. Then, you draw this straight line. The load line and the Q point change when either or both VB and RB change. The load line shown here is essentially the same as the load line for a diode circuit. Now, for the collector emitter loop, the load line is determined by writing KVL VCE is equal to VCC minus ICRC. And this KVL equation can be rewritten as IC equal to VCC over RC minus VCE over RC. Next, we set the VCE value to 0 to get IC value at y-axis and set IC value to 0 to get VCE value at x-axis. Then, we draw the straight line. Subsequently, we can find the Q point from the DC load line. As in the previous analysis of input loop, the input current IBQ is equal to 15 microampere. Hence, the Q point is the intersect value of IVQ and the DC load line, and from there we can find that ICQ is equal to 2.9 milliampere and VCEQ is equal to 4.1 volts. That's end our discussion on BJT DC load line. Don't forget to like and share this video.